please kindly launch your ASPEN if you haven't done that. All right. So now let's read the problem that we are going to do today. So the problem says pure 2,2,4 trimethylpentane produced at a flow rate of 1,000 kilogram per hour and 2 bar from an upstream distillation process needs to be cooled from 85 degrees Celsius to 20 degrees Celsius before it can be stored in a tank. Cooling water at 25 degrees Celsius and 1 bar is available to provide cooling. Choose Wilson model as the property method and do the simulation. So in this example, we would like to model a heat exchanger to find out how much cooling duty is needed to get 2,2,4 trimethylpentane to the desired outlet temperature, which is 20 degrees Celsius, and how much water will be needed to provide this. Okay. So this is our problem. We will start soon. So just as we have learned heat exchangers in heat transfer, you will learn heat exchanger. Yes, and energy balance, that's CPC2. You'll get into contact with energy balance. We are supposed to learn how we can use this simulation to model it. All right. So the basic form before we start, just as we have learned from day one how we enter chemical components, I want to give you 2 minutes so that you enter your chemical components and choose your property method as Wilson, and let's switch to the simulation environment for today's week. Okay, so let's move on as you keep on doing it so that you can follow. So I'm just going to enter my chemical components. So I'll use the alias section H2O for the water, and out of 2,2,4 trimethylpentane, that's C8H H18-13. Okay, so I have done this one before to see that ASPEN has classified it is an isomer as C8H13-13. That's why I entered it directly. Yes. So I'll give a name to this as water, and I'll name this one as petrol. Then I'll use the next two, and I'll choose a base method to be Wilson. Okay. Go to next and run. All right. So there's no warning. Table has been generated for it. Then we can switch to the simulation environment. Okay, so before we start, I want you to go to the setup and give a title to what we are doing. So just as we learned on the first day. So I'll give name to it as Bootcamp Day 3. Okay. And the description, I'm going to paste the problem that we are solving today to the description section. Okay. Yes. So let me show you this. This valid phases section describe the available phases, that the phase that we are working or doing our simulation. If you leave it blank like this, ASPEN will use its default phase, that's vapor liquid. If you choose vapor alone to be there, if you choose vapor liquid, ASPEN will take it as well, or vapor liquid liquid. So since we are dealing with vapor liquid problem, because the petrol that we are having at that temperature exists in vapor liquid phase, so we will leave it as a blank so that ASPEN will use its default valid phases, that's vapor liquid, so that we can move on. Or if you are done with that, you can close the setup and come to this session. So heat exchanging equipment that we use to add or remove heat from products or materials are at the exchanger session. So we have different kinds of them. We have a heater block, we have a heat X, we have M heat X, and we have heat X plus. Okay, so we are going to make use of heater and heat X. The heater is a shortcut model that doesn't demand a lot of detailed inputs before it can execute your work for you. So normally we use it like a cheat code to get your heat duty, then you use that one to model heat S or M heat X and heat X flux. And heat X is a detailed one that can allow you to do the normal heat exchanger modeling. That means you have a heat exchanger and a liquid stream or a heat stream is coming in and leaving out at a lower temperature, and a cold stream is coming in and it is also leaving. So we are going to make use of these two, and I'll make sure we make use of another thing manipulator so that at the end we are getting things one by one and we move. So I want you to put your heater block at the main flow sheet and give it a name. So I'll call it heat exchanger HE-01. Okay. Now I'll show you how we deactivate the insert mode. So I'll use escape to deactivate it. I want to enlarge my model and put this one inside. Okay. So now I want to join the streams. So I'll connect it to this one. Then I'll give it a name as petrol-1, P-1, then P-2. So before we continue, we all know that a heat exchanger will not work like this, like one stream inside and another stream outside. There is a shortcut model which is going to use an electricity utility or something that has been embedded in ASPEN to provide the cooling for you. So after this one, then we are going to model the detailed one, which is what we have always been seeing, that you have hot side coming in and cold side coming in. Then at the end, we get our desired cooling and heating. So once you have been able to do this, I know you can move on and specify. Let's continue. So the feed stream is a pure petrol, that's 224 trimethylpentane, and the temperature was 85 and the pressure was 2 bar. So I'm going to specify the mass flow rate was given, so was 1000 kilogram per hour. 1000 kilogram per hour. Then we move to next. So the next, this section is the heater block section. So you can specify the temperature. That will be the temperature of your outlet stream, and you can specify this side. So this one works in a dual nature. The pressure side, let's specify the temperature. So we want to achieve 20 degrees Celsius. Then you come to pressure side. So this side, you can put in a value there, and that will be the outlet pressure. But we are assuming that there will be no pressure drop in this process. So you can type in 0. So this one can represent a pressure drop and an outlet temperature. So if you want to specify it as a pressure drop, you just type negative the number so that the pressure will be subtracted. But because there is no pressure drop for this, I'll type 0, then we move. Okay. So now the sky is blue, everything is okay. We can run the simulation. It's a simple simulation. So you run, set up, okay. Okay, so there's no errors for this. So now we are done with this simulation, so we can view our results. So I'll add this and go to stream results. Okay, so the product one, this is a in liquid phase, this is also in liquid phase. Okay, and now we can see that the temperature has changed. That's moved from 85, now here is 20, and we can check out the heat flow. That's the enthalpy flow, kilowatts. Yes, and you can see that. Now let's check the main results for the exchanger. So you select it like this, you right click and go to results. Okay, so now we can see that there's no pressure drop. Total liquid is 1, the outlet pressure is 2, the outlet temperature is 20 degrees Celsius. Now the heat duty, the amount of heat that was removed is minus 41.6955 kilowatts. Okay, and you can relate it why it is minus. When you are cooling a heated something, we are just removing, so something exothermic process that we are doing.
Yes, my the heat duty I had a different value. I
Okay,
don't know if yeah
all right. So
was
the difference in okay, what did you get?
was negative 18.9128 kilowatts.
So now you are using which version? I guess it will be a higher version.
Yeah, version 11.
Okay, so version 11, and you did everything as I did it. The answer will be quite a bit different. I have version 11 here. Answer, Amos, check check your simulation, your inputs again. Because I'm having a version 11 here, and I'm getting a similitude of the heat duty that I had here. Okay. Please, can you? All right, Janet. Those who are using version 11, please, can you give me your heat duty? You can type it at the chat section, or you can read it. Okay. All right. So I'm having the same thing as you, Emmanuel. All right. Oh, Janet, I didn't see the unit. Okay, Trump, kilowatts. All right. Okay. It doesn't vary that much. Thank you. Okay. So now we can continue with the advanced one. I think today I'll make sure I show how you can use it to draw. Okay. Somebody had a question. Gilbert. Okay.
Clinton, I've seen it.
Okay. Okay. You have seen the error. Thank you. Okay, Gilbert, can kindly go over for we who joined late. Okay. Can I see where you are lagging so that I can go over? That's why we are here, so I'll help you.
Yeah, I'm trying to find the conditions for the inlets
Okay. So let me
stream.
paste the question here again for you. Right. Right. So I've pasted the question. Yeah, you can check it out and you see the conditions for the inlet. Yeah. Remember, it's a pure compound. All right. Thank you very much. Okay. So now let's go to the main flow sheet. So let me clear my screen. Uh, okay. So now go to modify and try to bring the temperature and pressure on your screen just as I'm doing. Okay. Now I want to show you how you can, because now all these values they are rounded values. So how do we bring decimals to it? How do we add the decimal corresponding decimals to it? So go to the results, stream results at the modify section. There's a small arrow pointing
Clinton,
southeastern. Yes.
sorry, I have a little challenge. My values are showing in PSI and pound mass per hour, so I always have to change it. I don't know if there's a way I can.
There is right.
Yes, please.
Okay.
And if I even come back to the simulation environment and I modify to show the temperature and pressure, everything is showing in PSI and
All right.
pound
So
mass the fluid. Yeah.
just go to home,
Okay.
right, and locate units.
Unit. Okay. Okay.
You can make it change it
Metric.
from, yes, from ENG or MET and make it MET C bar.
Met Siba. Okay. 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 Oh, yes, please. Thank you.
So
Okay.
now go to modify and the stream result, the arrow pointing southeastern part, click on it to bring you to this section. So you can see temperature has been checked in, but it is percent point zero F. So now the number of decimal place that you need, you can clear the zero and put it there. So I want to get three decimal places. So three. Then I'll check this. Three. Let me check in the vapor fraction. It's already two decimals. So I'll make it three. Then go to move flow rate. Make it three. Mass flow rate. Three. Volumetric flow rate. Three. Heat duty. Three. So when you are done like this, just click on apply and okay. All right, so it looks like I've checked in everything. This is the key is here. I've checked in everything, so let me clear them. All right, All right, so let me go over again. So now I want to, so for you to allow decimal places to be part of your displays result on your flow sheet, what you do is you go to stream results here. Stream results, check version 11 if is that. If you are using version 11 and you can't find it, you can go to file and move to options and look for flow sheets. You can find it there and change them. So you stream results, then you come to what you have checked in. So I have checked in temperature. So where you have percent symbol point dash F, you have to clear the any number that's there and type your desired number of decimal places today. So here I want you to be 3 decimal places. When you are done, you click on apply and okay. Ima was asking about the amount of water that we are going to use. So in view of that, we have to use the advanced or the detailed model. That's what we are going to use. And I don't want us to close this window and open a new one. We can modify it and do it. So we are going to make use of manipulators here. Manipulators. So click on manipulators and look for duplicator. That's DUPL, duplicator. So once you pick the duplicator, bring it to the main flow sheet and give it a name. So I'll name it dupe. I'll name it dupe. So now we are going to duplicate. So bring it back a bit. We are going to duplicate the main flow sheet, the petrol P1. I don't want to get a different one. So how do we do this? So now that I have my duplicator, I just reconnect P1 to the duplicator and use the product stream to send the duplicated results of P1. So just reconnect it as know how we reconnect. Right click on it, go to reconnect to destination, put it to the duplicator, then click on material stream. I think I showed you how you can label it. So click and hold to bring the stream up like this and send it to the first one. Give it a name. I'm going to name it P1, not P-1, P1. Then I'll connect the other one that will be going to the main heat exchanger. Then name it P2. All right. Then after that, because it's the same feed, I'm going to hide the IDs. So click on the stream, right click it, go to hide and go to hide ID. So now you will not see any indication on it, just the same thing that's going in. So you click on P2 as well, go to hide and hide it. So once we are done with this, it means we have our material stream being duplicated. Now let's go to exchanges. Pick heat X,
Clinton,
please.
please, can you go over? Some of us lost touch a little.
Right. So we are going to use a duplicator. So I said you go to manipulators, then locate duplicator. So you see duplicator here. Duplicator, just select duplicator and bring it here. So let me start all over again and delete my duplicator block. Okay. So now I select duplicator, bring it to the stream, the main flow sheet, then give it a name, DUP. Then I'll reconnect the streams to it. So double click, connect it to it. Then you double click, then you reconnect to source. Double click the back arrow to reconnect to source again. All right. So once you are done, you right click, Control A and align to straighten them for you. So if you are using version 10, go to locate, choose modified, locate where we have the stream resource, and look at a small arrow at the right side corner. We'll click on that. Then a new window will open for you like this. So now this is a temperature that has been checked in. The number of decimal points is the number after the percent symbol dot. So if I need 3 decimal places, I just delete the number there. So I select it, I just delete the number there and type 3. So when you are done with that, you click on apply. Okay. So now that we have duplicated it, run it. Okay. But when you run it, you see that it will be the same thing that's at P-1. That will be the same thing that will come to the other stream that we have generated. So we are going to use that one to model the detailed one. Okay, so let me see the question. So basically, you use duplicator when you want to avoid stress of entering the information of the input stream for the new model. Yes, please. Okay, so now let's bring a heat S model to the main flow sheet. So click on heat X, bring it this side. Heat S. So I'll name it heat exchanger -02. Okay. So now we are supposed to connect streams to it. So please note, this is a hot stream that we want to cool. Oh, I'm going to reconnect it. Just look at where it will be. Double click. You have a red one here, which is required. Then this is required. But this one is a cold required, the cold stream that you are bringing it. And this one is a hot stream that you want to cool. So we connect it to the hot required. Okay. Now let's bring our streams. So now this is the hot that we will be discharging out. So the hot stream that we have sent in, it will come out as a code one. So just specify it here. So this will be the petrol that will come out. So click on that and give it a name. So I will name it P dash, or let me name it petrol pet -1. Okay. Now we have to bring a stream for the water. So click on what this one. This will be the code required, and give it a name as water -in. Then this will be the water that will come out. We give it a name, water out. Name it H2O out, so that it's 8 characters, not be more than that. Then I'll rename this as H2O in. Yes. So now let's move on. So we have to go to next to specify the next thing you have to specify. So now it has bring us, we have put in a new material stream. So now we have to check in the temperature. The temperature of the water given in the problem was 25 degrees Celsius at 1 bar. And we were not given any amount of water that we are supposed to use. And we are now starting. So um, I would say let us use the same amount as that of petrol to do the work. That's 1,000 kilogram per hour. 1,000 kilogram per hour.
Please, I have a question. Did you specify the streams whose IDs we hid?
No, you don't need to specify. Those
But
streams,
when I click on next, they are okay.
do you understand it now?
Yeah, but when I click on next, they're asking me to um specify those streams. I don't know.
Really? Then check it very well. Maybe
Mm,
I guess maybe it has been connected.
oh, okay.
Check the connection and reconnect it.
Okay. Okay. Sure.
Okay, so now let's move on to next for the next thing that we have to specify. So this is the detailed or rigorous specification that we are supposed to make for the heat S. Before we let ASPEN give us some predictions that we have to do, I want us to design this one again with a shortcut approach. So you can come to the model fidelity here. You see that we have shortcuts. Then we have hot fluid. So hot fluid, where do you want it to be? Should it be inside a tube or it should be in the shell? And we have a shortcut flow direction. That's counter current or full current. All right. So the calculation mode, we are going to leave it at design. Then this is the specification, heat exchanger specification. So we are going to choose one of these to do our work. Now, what we know is that we want to achieve 20 degrees Celsius of the petrol. So when you come here, these sentences, the one that describes what you want to achieve, that's the one you select. So we have hot stream outlet temperature. Now we know the hot stream outlet temperature to be 20 degrees Celsius, so we can select that. If we knew the cold stream outlet temperature, we could have done that. You can also use hot stream temperature decrease to also do that. But now let's select hot stream outlet temperature. And it will ask you what's the figure, and it's 20 degrees Celsius. Then it will ask you what's the minimum temperature approach. The minimum temperature approach is the minimum temperature that can be exchanged between streams. According to research, it's noted that for many companies, heat exchanger designs is from 5 to about 20. So we will select it to be 10. I'll choose 10 for this. Then when you are done like this, you see that everything is okay. We don't have any knowledge on anything on logarithmic mean temperature. All right, so we are going to leave it just like that. Pressure drop, no pressure drop. Then we will run. After that, ASPEN will give us a design. We'll run it. All right. So don't be afraid if you are getting errors. It's okay to get error. Then we work from errors. Okay. Okay. So we can read the error equation to see what is happening. ASPEN will not do anything that violates engineering laws for you. Yes. So let's read the results. Yes. Okay. So my results, I don't know if it is the same thing as your own. I'm having invalid hot stream temperature. That means the temperature specification is less than that I need, and hence I'm getting zero heat duty at the curve. We are going to use sensitivity analysis to do that, but that's a topic for another day. So what we are going to do now is just go to the setup again, double click on it, go to the setup, change the minimum temperature approach to 5. When you are done, don't run it. Go to the water in material stream and change it to 1500. Oh, sorry, it's supposed to be in kilogram per hour. 500 kilogram per hour and run. Okay, the error persists. What's this error? Okay. All right. Okay, guys, we are getting thermodynamic errors for the work that we are doing. So, in order for you to do it, I want you to change the minimum temperature approach. These errors will be addressed next day when we are doing fitting sensitivity analysis and other model analysis tools. So, go to your heat X specification and change the value of your hot stream temperature to be 40 degrees Celsius, and the minimum temperature approach make it 5 and run. I guess you are supposed to get a result. Okay, so now we can see that we have gotten a result. So just select your heat exchanger, right click on it and go to results. Or when you go to results, check summary. So here it's going to give you a rigorous detail, or you will see that you have inlet and outlet streams and the stuff that are happening. You go to exchanger details, is where I need. So you see that ASPEN has estimated the required heat exchanger area for you. So my people that will be designing heat exchanger, this can help you, it can guide you so that you get your heat exchanger area. There is a shortcut, and so it will help you. And you see that the LMTD, logarithmic mean temperature difference, has also been calculated for you. You can use the manual calculation to check to confirm. If it is not the same, it will be close. Okay. All right. So once you are done with this, I want ASPEN to suggest a proper design for us. So double click on it like that. And instead of shortcuts, click on shell and tube. All right. So as you click on shell and tube, you will see that a new window will pop up like this, and shell and tube has been selected. So we go to convert. So it is going to convert everything. So hit on convert as we wait for it to convert the space to ASPEN energy exchanger design. All right. So when you convert it, it will bring you to this side, EDR. Here is where we design ASPEN in detail, the heat exchanger in detail. Sorry. So here we have the thermal type that has been indicated already. We are using B, E, and M type. All right. So now the hot fluid is now in the shell side, which is not advisable. We are going to put it in the tube side, and the tube pattern. So you can choose the tube pattern that you need. You can put it at 30 triangular or the squared one. And we need baffles within it. And the material that we are going to use for our design, carbon steel, let us change it. I'm going to change it to something like aluminium. All right. So I'll choose aluminium. You can choose carbon steel to be fine. And if you have data for inlet diameter and outlet diameter, you can check in yes and specify them. But if you don't have, just keep it at no. So when you are done like that, all that you have to do is to just hit on size, and ASPEN will give you series of design and give you an optimum one. Or if you are done with this, so we kept everything like that. We changed the location of the hot fluid to the tube side. So we are putting the hot fluid in the tube. Then our tube pattern is still the same as the default one ASPEN gave it to us. And we have the tube outlet diameter being here and the pitch also being here. So now let's size. So ASPEN, as we wait, it's just doing optimization. Run has started, and it will just it will do series and pick the best design for the stuff that we have done. So now it has suggested close. Okay, 7 designs are near to our prescription, what we need. So you can see that designing. Okay, now it is done. We change the question, and so this is the result that we are getting. So you can see that ASPEN has augmented everything, and later on it is giving us a certain plan, and we can get the layout of the tube as well. And you have the stream temperatures also here. All right, so once you like this design that it has been given to you, so you can see inlet, outlet. So this will be the inlet. Yes, so our inlet was here, outlet will be here. We add the water to this side, and we take the water out from this side. So once you like this, you just go to accept. If you don't like it, you go to redesign. So you accept design, and it will take you back to your main ASPEN window. And now that you have accepted it, you have seen that the calculation mode has changed from design to simulation. Now it has changed everything for you. It is now a tube, and it has selected a counter current already. So let's run it. All right. So once you are done with this, your results is available. You can right click on it, go to results to see the stuff that has been provided. Okay, so the same things are still here. You can see that now earlier the stream results was the LMTD was around 26 something, but now it is 20.19, okay, by the design that we chose. So once you are done with this, we can go to geometry. All right, let me show you the design that ASPEN has done for us. So you come to the navigation pane, locate geometry. Okay, I want to show you the drawing that has been given by ASPEN. Okay, right. So this is a thermal resource. Okay, so go to EDR shell and tube resource at the navigation pane. EDR shell and tube resource. So now it's not just any shortcut, it's a shell and tube resource, and you see detailed design data that has been given. So let's go to settlement plan. Okay, so this is the diagram that was shown to us. We have the tube layout per our design. This will be the number of tubes, and this is the temperature stream plot. Temperature stream plot. So you can save this just as um, we save the main flow sheet. So just go to file, go to save, print. Where are you? Okay, so how we save this, you just right click on it and go to print, then it will print it for you. But you know, we are printing it to PDF, so you print it. No, it's supposed to be portrait, then I print. So a name will come, my design D1. Then the tube sheet, you can also print the tube sheet by right clicking on it, and you get a tube sheet print option, then you print it just like that. Okay, so people, this is our detailed heat exchanger model and the shortcut model.
Clinton, I think I missed something.
Okay,
The last stream,
the
the temperature value is different. Yeah,
your last stream.
yes.
Which,
It's
what is the name
42.
of your last stream? Okay,
The water
what do you
out
have?
75,
You have
which is
75. All
yes.
right, so I changed the flow rate to 1500.
Oh, okay.
All right,
Of the heat X
the water
of the water in.
mass flow rate.
That stream, the water out. Say you change the flow rate of water in 2500.
1500.
Okay, so let me do that.
Save your ASPEN file like this. So you go to format, then you select text box. So when you go to format, it will just be like Microsoft. So you just select text box. You can write your name. So my name is Obimenu Clinton. Obimenu Clinton. Then select a text box again. Write the heat duty. For the first one, heat duty. Okay. Then the next one here, write the corrected LMTD. So you select it just as you use Word. Then write the heat exchanger area. Heat exchanger area. Yes. So when you are done like this, then uh, save it. as PDF, go to print, then you print to PDF, then you can save it with your first name, Clinton underscore day 3, then you save it.
Please, on the flow sheet, you said like when we use the format to add the text boxes, that are we adding the value to the name like the heat exchange area? You add the value to it before saving it,
Yes,
right?
yes.
Oh,
So if you look at how I have done my own, um, where I have written heat duty, you can type heat duty. Then you look for your heat duty resource. So you click here,
okay.
go for heat duty. So the heat duty resource here, I'll change it to kilowatts. So just copy, you can copy it, or you just type up to 3 decimal place. I'll copy it like this, or it's, yes, so 40 minus 41.69, then you come here, heat duty equal to minus 41.6955 kilowatts, like this. So when you are done, then you save it and submit it to the page. Is are you okay? All right.
Okay. Thank you.
Thank you very much. All right. So today, this is where we will bring the heat exchangers. We are supposed to use sensitivity and design specification, but because this is an introductory course, I will not start like that. We want to go on a slower pace so that we can get whatever we are doing. And later on, when we get to the plant wide designs, then we are going to employ all the heat model analysis tools and sensitivity tools. So thank you for joining.